Okay, so the next bit of the course is calculus stuff. So we'll start off with the differentiation. So remember from last year, and I'll just go through this from last year. So the average rate of change is the gradient between the 2 points. So if we've got something like this, for example, and we've got a curve, for example, that goes like that, and we've got two x values, A and B, so we would have some points on the line. So we'll have a point here that we'll call point A, we'll have another point here that we'll call point B. Then the average rate of change is the gradient of the line that joins them. Alright, so the coordinates of each of the points, the coordinates, if that's some function fx, then the coordinates of the points would be A, f of A, and B and f of B. So the average rate of change is the gradient. So it's the gradient of line AB. So as we know, y2 minus y1 thanks Ethan, over x2 minus x1, and so that would be the average rate of change. Alright, now if we want to take that and try and find out what the instantaneous rate of change or the gradient of any time, what we can do is we can move this point B closer to A, and then the line joining A and B will be closer to the tangent at B. And so that's what we would call our instantaneous rate of change. I want to rub that off and draw another. Oh no, I'll do it down here. So instantaneous so I'll draw another curve. I'll just draw this, curve it around this way, doesn't matter which way it curves. So again, we've got a couple of points on it. Point A and point B. And gradient of our nice wobbly straight line there. Much better. Alright, so if I wanted to know, for example, what the gradient here is at A, so the gradient curve there, I could bring point B closer and closer, down here further and further. So if it was down there, the gradient would then be that. If it's there, it's there. And finally, when it gets really close to A. So what we can do is we can relabel these in other ways. So we can say, alright, if the distance between here and here is h, then b of course will be a plus h, and so as we bring point B down, so making H smaller, we get closer. So how do we write that? So as H goes towards 0, point B goes towards point A, and the gradient of AB goes towards the gradient of the tangent A. And the gradient of the tangent at A is the instantaneous rate of change. So the way we can write that is we can write that as that the gradient, the gradient at A would be the limit as H tends to 0 of the Y value, f of A plus H minus f of A over H. And that is known as the derivative, this thing here is known as the derivative of the function. So if our function is f of x, then this here is known as the derivative. All right.
What's m?
M is the gradient. So this is known as the derivative of f of x with respect to x and it's written, yep,
What's in between M and A?
at. So gradient at A. All right, so we write that derivative of as f dashed x. Now, so more generally, f dashed x is the limit as h tends to 0 of f of x plus h minus f of x. All right, so if you can use that thing to find the derivative, and we did that last year, and that would be what's called first principles. However,
Oh, they're up the bottom bit. Thank you.
however, there are some relationships.
What's that?
Now, fortunately, there's patterns, and we're going to use patterns. All right.
Ever have to do it by first principles?
Not this year, no.
Thank God.
Really?
Really.
So why did they teach you it?
Why?
To understand the
Yeah,
basic
to understand that the connection between the gradient and the derivative. because the derivative's got from working out the gradient, bringing that point in closer and closer. As you get closer and closer, it gets the gradient of the curve at that point. So we do it so that you get that connection between the two,
That's the-
rather than me just writing up and saying, this is differentiation, do that, and that tells you the gradient. We go, how do you get that? But at least with this here, if I've got this here, we want to know what the gradient is there. If there's a point there, bring the point closer, bring it closer. So as this bit here, which is h, gets smaller and smaller, then the gradient of this line gets closer to the tangent, gradient of the tangent. So there's a direct link between that and the gradient. And then by doing this, then it was noticed that patterns existed. So the patterns didn't come about first, and then this happened first. Then there's patterns. If there's patterns, we're going to use the patterns, not this, because we did it last year and it's time consuming, yeah?
Yeah.
You don't have to.
All right, so it was kind of a developmental process. All right, so fortunately patterns exist. And we're going to use the patterns. So first of all, derivative of x to the n is what we're going to look at today. There's patterns for other functions and we'll get to some of those, but we're just looking at x to the n. All right, so the pattern exists here. Is the following. When you differentiate to get f dash, the old power, which is n, comes down out the front and multiplies as a coefficient. And the new power is one less than what it used to be.
Oh yeah, I remember this stuff.
All right, so what else have we got? Some examples. Alright, so if we've got, like this one here, we've got a coefficient out the front. We still bring, which means 5 times x, of course. 2x to the 1, which is 10x. Alright, so if the coefficient's already there, it just gets multiplied by that power that comes down. If we have things that where there's a number of terms, like so,
3x squared plus 2.
3x squared plus 2 would be exactly what we're looking for. And the same if there's a subtraction. Now the only thing I haven't looked at is if we have something like this. so the 2x to the power of 4 becomes
8x cubed.
8x cubed, and the 5
0.
becomes 0, yeah. So any number by itself, and you differentiate that, it's 0. Alright, so what can we use this thing for? So, important to remember that the derivative tells us about the gradient. So, this derivative here, f dashed x, yeah, it's 8x cubed, but it tells us about the gradient of this. So if we wanted to know the gradient of 2x to the 4 plus 5 at some particular spot, we would put that x value of that particular spot in here, and that would tell us what the gradient is.
Oh, really?
Really.
There you go.
There you go.
That would have been a lot easier to do last year.
Would have been a lot easier to do last year. All right, so let's have a look at that. So the gradient of the tangent. Oh, it's a subhead there. All right, so the gradient of the tangent, just write what I just said.
This is one of the other patterns, right? Is this one of the other patterns?
Oh, we're just going to look at x to the n's at the moment, and we'll look at other functions later.
Don't get your head sucked, Carl. Thank you. I think you're getting a bit dramatic. Don't look at me.
It's like day 4 of Utah.
Oh, did she survive? Did she come back to the same person she did?
All right, so if we want, for example, just simple cubic, if we want to know what the gradient of 0.11 is,
Is that an example?
No.
oh yeah, I guess it is.
Oh, Mr. Tina, you've just
What?
ruined my summary book.
Oh no,
I've never written an I in red pen before, but I've just done it.
oh
Would
no.
you like some wine?
No, that's alright.
You're going to be able to get over that, Clint.
I think I'm going to fail my methods exam because of
Just
this.
because of that? Oh no.
It's very possible.
I mean, I don't understand how you're prepared to read out of this. That might be the real question.
Read my summary book, she's fine.
Sure.
All right, so the derivative, 3x cubed, and it's at 0.11, and so here we've got the x values, all we need to worry about, because the x value is in here. So if it's 3x squared, and the point's 1, the x value is 1, put that in, so the gradient of the curve at that point is 1, 1. All right. All right, what else? Okay, so I've just written this in function notation, so fx. Need to know other notation. And you need to be, it doesn't matter which one you use, however, you need to use the one that's appropriate for the question.
What determines it? Like, is it just what's in the question, or like?
Yeah, what's in the question?
Okay.
If the question's written at f of x, then you write this. If it's written y equals, then you write what I'm about to.
Oh, is this dx dy?
Correct. Well, other way around, you almost.
dx.
Yeah, dy dx.
Do you have that one around your waist? I think I want some really.
All right, it's just two different people, different parts of the world doing stuff, and both have different ideas of how things should be written. All right, and you can use any letters, whatever. So, for example, if you have y equals t squared, for example, then you need to write the derivative in terms of the variables you've got. So dividing t, yeah.
Can we just e to e, 6e to
And so it's equal to 2t. All right.
Did you just rub off the I bit?
Because here it's y equals t squared. So instead of x, we've got t. So if we want to, we'd write it as dy dt, derivative of y with respect to t. So use the same pattern. Bring the power down, reduce by 1.
How much? He went feeding it, surely. How much is it? How much did he offer for you? How much did he offer?
I would have to go.
Are you going to sell it to him?
Think about it. And there's a Facebook like group and they sell for 600
Put a left kid on that.
No, like, some people just want it for some reason, it's just ridiculous.
Alrighty. Now, ones like this one here, you need to change things around a bit first before you do the differentiation. So what do you notice about the numerator here? There's an x, which is, so I could rewrite the numerator as,
X outside, and then x plus 3.
right, what do you notice then?
And you can cancel out the x on the bottom, and then you've just got x plus 3.
All right, and so now we differentiate that, which would be 1. Yeah. All right, so sometimes you need to rearrange things, cancel things, factorise so you can cancel. Now, also another way things are written is like this. It's like this. So rather than writing dividing x or dividing z in this case, because we've got z rather than x, if something's written like this without anything there, it means to differentiate this with respect to z. So when we do that, we would get what? Ten z take
Why is there no number?
sorry.
Why is there no number on
Why is there no number?
top? Like, why is it just D?
Right. When they put the function in bracket, that's just the form that they use. So rather than writing y equals 5z squared minus 4z and then find dy dx,
They just write it that way.
just written this way, yeah.
Then if you're writing the answer, what would you say?
Just write the answer like that.
So you can't put anything.
You don't put anything in there, you just say it's equal to that.
So that's the same as differentiating.
It's exactly the same. It's the same as if I had written y equals this, find dy dx, you'd say that dy dx is equal to 10z minus 4. Exactly the same. Just written in a different way. And you need to be aware of the different ways that it's written and know what they mean, how to interpret them. All right, because this is reasonably common to have something written like that. All right. The next bit we can use this for. Another subheading.
Yeah, we're just saying that like the differentiating the dy dx, the y equals 5, is this very much is the same as
Is that better, Zeke?
Yeah, that's better, thanks. It's more mine, shows the
All right, another subheading. All right. So if I have a curve and we've got a point here somewhere, there we go, there's a nice point right there, and I've got tangent, goes like so, and we are interested in the angle between the tangent and the x-axis, so we're interested in this angle in here, call it alpha. So can anyone remember what the relationship between the green line, the gradient of it in particular, and this angle in here is? Tan, yeah. So recall
How many chapters are we doing here?
3.
Haha, so we said it's just one chapter.
No, it's just a bit
Oh, no.
Like they're pretty, you're right, pretty good.
it's a bit rude, I think.
Inside.
I don't need to ease us into differentiation.
So just a brush, it's not doing anything.
No, look, I'm not sure about you, I sucked at this last.
Yeah, same, but like, I'm actually paying attention this year, so
I know, but
it's a
still
little
like,
bit less harder.
I'd like more time to,
Process it.
I also don't have much more room.
All right, so if the gradient of that green tangent is equal to tan of the angle it makes,
Is that X there? This is
Which
in green?
no, that's an alpha.
Look
Or
at
that
that
little
little
zero?
It's like a little fish,
big bold lens.
it's a fish.
Now, how's that?
Isn't that thing like isn't that like introducing chemistry, like applying relationships, like direct correlation? Do you think we just learned chemistry?
Sorry,
Yeah.
No, like assisted.
All right.
We did it in your
Yeah, but did I listen to you?
You can tell that I tried.
No, I did not. Why don't we start using this symbol? Why don't we just use like one of the ones we've already got?
Oh, because
Like this, what's the theta circle with line in it? I don't understand. Like how they can't choose the same symbol as represent line. You will say that example in your patient home.
all right. So, question: find the coordinates of the point on the curve. So, like here, for example, coordinates of that point on the curve, and the curve is the blue one, x squared minus 7x plus 8. Where the tangent, there's the tangent, the green line there, makes an angle of 45 degrees with the x-axis. All right, so what we know is that the derivative is the gradient of the tangent and the gradient of the tangent, gradient of the tangents
The gradient one.
is gradient is 1. All right, so we know that m equals tan 45, which is equal to 1. But we also know that the gradient is the derivative of dy dx. And dy dx is 2x minus 7. And it is, yes, correct, it is also equal to 1.
So rearrange that to get x, please.
So rearrange that to get x. So 2x would be
Equals 4.
equals 4. And we were asked for the coordinates. So we found the x value, so we need to plug it in. So y would be equal to 4 squared minus 7 times 4 plus 8. When you do that, you get negative 4 apparently. And so the point on that curve is 4 and negative 4. Right. All right, next subheading. Two more quick things.
There's more, Nicole. Sorry, Nicole, I've also just reached the end of my page, so.
All right, the sign of the derivative, when we talk about the sign of the derivative, we mean positive or negative.
fixing for a couple of days, but it's like half a clock.
So if it's positive or negative, and the derivative tells us about the gradient, then the sign, whether it's positive or negative, is going to indicate whether the gradient is positive or negative.
Mr. Boarding for very bad.
I didn't care.
No, no.
Oh,
Personally, I thought it was a nice jumper, but I was not going to say anything on this. It was
yeah, I know.
ruining to you.
Who was?
This is all.
It was pretty much just bullet Ethan
She
there.
was.
I'm gonna get up and like full on have a crack at it.
She was not happy.
She was losing the plot. I was just trying to figure out what the hell was going on.
Every other class is what? Well, I'm not this stupid shit.
Oh, not the scale.
That in front of those.
Right, so here's a graph. So this could be a multiple choice kind of question. You've got this, and then you've got your graph, you ask this, and then it could be multiple choice answers. All right, so got to remember f dash to x is gradient. So in each of these, we're asked about the gradient. Greater than 0, so if anything's greater than 0, it is positive.
Yep.
So here we're asked about what x values is the gradient positive. So if I break it up like this, we go, well, where is the gradient positive? This bit here, and this bit here. Yep. So this bit here can be written as, consistent with using set notation, that's x is less than whatever that number there is, -1. And also So that's a union
What?
up here, greater than 4. So when x is less than -1, that's down here, so that's -1, and that's 4. So when x is less than -1 down here, then this graph has a positive gradient. When it's bigger than 4 over here, again, has a positive gradient. Alright, so equals 0 means a 0 gradient. So a 0 gradient would be flat like this. And whereabouts would the tangent be flat?
At the points.
At the turning points, yep. So again, just keep the consistent with our notation. It's the x values, and those x values are when x is equal to -1 and 4. And part C asks about negative gradient, and where is the gradient negative? In the middle. And again, to be consistent with our notation, we would write it like that. All right, so one of the things in the exam is that you write your answers consistent with how the question's written. So the question here is written in set notation, so you should write your answers in set notation. But what does it mean? It means you just put some squiggly brackets, this x with this colon there, and then put your other stuff in there. All right, last thing.
The chance of Bell's going to go after we do this. Bell is not even close to going. What is giving us like you
All right, negative index is the good news. Negative index is the same as positive index. All right, so
We're literally like on the same.
So we follow the same. So if we've got f of x equals x to the -2, find f dash to x. So it's exactly the same. So f dash to x. What do we do with the old power?
chuck it in front.
Chuck it in front, and the new power is
-3.
-3, one less. So if it was -2, it's now -3. Easy as that. All right, done.
Oh boy.
All right, so that's exercises 9A, B and C, and I'll give you the work plan because I'm not here tomorrow and Friday's pupil-free day, so that's why we've done 3 today.
What were your thoughts on moving the people free day from the gap dates to Friday, Mr. Sim?